Module 4, Lecture B, Tuples and Dicts. By the end of this lecture, you will be able to define and use tuples to store small, ordered groups of related values, create dictionaries to map keys to values and access items by key, and update and iterate over dictionaries to read and modify stored data. Understanding tuples. Tuple syntax basics. A tuple is an ordered collection of values grouped together as a single unit. Its elements are separated by commas, can be of any type, and their positions are preserved, so each item remains distinct and meaningful. This consistent structure makes tuples a compact way to represent related information, such as geographic coordinates or a student's name and ID number. In Python, tuples provide a concise and readable way to group a few related values together. You create a tuple by listing values separated by commas and enclosing them in delimiters, which clearly shows they belong together. The order of elements is preserved, so you can reliably access items by their position, such as the first or second element. Because of this ordered structure, tuples work well for representing small pieces of structured data, like a time with hours, minutes, and seconds, or a product with a title, price, and stock quantity. Tuples are a simple way to group a small, related set of values into one unit. You might use them to represent things like a building and room number, or the length, width, and height of a package. Because they are lightweight, tuples are especially useful for functions that need to return several pieces of information at once, such as a result and a status. Using tuples in this way helps keep your code clear, logical, and easier to maintain. Python code, tuple, syntax basics. We will introduce basic tuple syntax using simple, everyday examples, focusing on how commas and the order of items create small bundles of grouped values. You will see that a tuple is just an ordered collection where each position matters. By printing whole tuples and individual elements, you can clearly visualize their structure and how to access specific items. This helps you understand tuples as compact, ordered groups of related values. This comment explains that the script does not require any external libraries and uses only Python's built-in features. Because of this, you do not need to install extra packages to run it. This makes the code simpler to use and easier to run in any standard Python environment. Overall, it emphasizes the script's simplicity and portability. We create a tuple to represent a room location by combining the building name and room number into one value. Using a tuple keeps these two pieces of information grouped together as a single unit. Because tuples are immutable, they cannot be changed after they are created. This helps preserve the integrity of the room location data and maintains the relationship between the building and the room number. We use a tuple to store the dimensions of a package in inches as three numbers, 12, 8, and 4, representing its length, width, and height. A tuple groups these related measurements into one collection while keeping their order. Because a tuple is immutable, the values and their positions cannot be changed, which helps preserve the meaning of each dimension. We use a tuple to store a student record as a single unit that includes the student's name and a unique identifier. In this example, the first element is the name Alex Johnson, and the second element is the identifier 10234. The tuple keeps these two pieces of information together in a fixed order, making it easy to manage and access the student's details as one immutable record. We print the entire room location tuple to show how it groups related values into one unit. Seeing the full tuple makes it clear that the building name and room number are stored together. This helps you visualize the tuple's structure and understand that both pieces of information form a single, cohesive data item. This line outputs the entire tuple that stores the package size in inches. Showing the tuple makes it clear how the values are ordered and grouped together. It emphasizes that the dimensions belong together as a single, organized set of numbers representing the package size. In this example, we print the entire student record stored as a tuple. This shows that a tuple can contain different kinds of data at once, such as a name stored as text and an identifier stored as a number. By displaying the tuple, we can clearly see how these mixed data types are grouped together in a single, ordered structure. In this example, we are printing a specific element from a tuple called room location, which stores a building and a room number. By using an index of 0, we access the first element in the tuple, which is the building name. This shows that the position of each item in a tuple matters, and that indexing lets us retrieve particular values based on their order. In this example, we access the third element of a tuple that stores the dimensions of a package. That element at index 2 represents the height in inches. This shows that tuples keep the order of their elements, so you can reliably retrieve specific values by their position. Tuple indexing, therefore, lets you directly access any stored dimension based on where it appears in the tuple. This material introduces basic tuple syntax in Python using simple examples. It shows how tuples can group related values such as a building name with a room number, package dimensions in inches, and a student name with an identifier. When the code runs, each tuple is printed as a single bundled set of values. The script also demonstrates that the order of elements in a tuple matters by accessing specific items, like the building name or the package height, using their positions. Overall, it illustrates how tuples keep different pieces of data together while preserving their sequence. Tuple immutability explained. In Python, a tuple is an immutable collection, which means that once it is created, its values cannot be changed. This is different from other collections that allow you to modify their contents. Because tuples stay the same, they provide a stable way to store data, such as coordinates or configuration settings. Their immutability helps keep data consistent throughout a program, making them useful for small, ordered groups of values that should not change after they are defined. When working with tuples, it is important to distinguish between changing the tuple itself and changing the objects it holds. A tuple's structure and the positions of its elements are fixed once it is created, so you cannot add, remove, or reorder its elements. However, if a tuple contains mutable objects, such as lists, those objects can still be modified elsewhere in your program. For example, a tuple might store a user's name, ID, and a list of actions. And while the tuple stays the same, the list of actions can grow or change. This shows that immutability applies to the tuple's structure, not necessarily to the contents it references. Tuples are immutable, which means that once you create one, its contents cannot be changed. This makes them useful for sharing data across different parts of a program without worrying about accidental modifications. Python code, tuple immutability explained. We want to demonstrate that tuples are immutable using simple, beginner-friendly examples. The key idea is that you cannot change the tuple itself, such as replacing one of its elements once it has been created. However, if a tuple contains a list inside it, you can still change the contents of that inner list, even though the outer tuple stays fixed. By printing clear messages before and after these operations, you can see that attempts to change the tuple fail, while changes to the inner list succeed, showing what changes and what remains unchanged. The commented line with the pip install command is simply a placeholder to show that certain libraries may need to be installed for the script to work. Because it is commented out, it does not run automatically, but instead reminds users to install a specific library if required. This is a common way to indicate dependencies directly in the script, so they can be set up before the code is executed. We create a tuple using two floating point numbers to represent a fixed geographic coordinate, with one value for latitude and one for longitude. This tuple is meant to stay the same, demonstrating that tuples in Python are immutable and their elements cannot be changed directly. We then print the coordinate to show the original values it holds, reinforcing how tuples preserve their contents once they are created. In this example, we try to change the first element of a tuple called coordinate, but this is not allowed because tuples are immutable. The assignment is placed inside a try block so that any error can be handled gracefully. When Python blocks the change, it raises a type error. The except block then catches this error and prints a message explaining that items in a tuple cannot be modified, along with the error details. We create a tuple called a user record that holds a name as a string, an identification number as an integer, and a list of two strings representing actions. This example shows that a tuple can contain different types of data, including a list. We then print the entire user record to show its initial state. The key idea is that the tuple itself cannot be changed, but the list inside it is still mutable and can be modified. In this example, a list is stored inside a tuple, and we add a new action called purchase item to that list. This shows that even though the tuple itself cannot be changed, the list inside it can still be modified. After updating the list and printing the tuple, the overall tuple structure stays the same, but the contents of the inner list are different. This illustrates the difference between the immutability of the tuple and the mutability of the objects it contains. The code uses a built-in function that returns a unique identifier for the user record tuple to check its identity in memory. This identifier stays the same as long as the object exists. By printing it before and after changing the contents of a list stored inside the tuple, the code shows that the tuple itself is still the same object. This demonstrates that the tuple structure is immutable, even though it can contain mutable elements whose contents can change. This script illustrates how tuples in Python are immutable. It first creates a tuple of geographic coordinates and shows that trying to change one element causes a type error, meaning the tuple itself cannot be modified. It then builds a tuple that includes a name, an ID, and a list, and demonstrates that you can still change the contents of the list by adding an item. Throughout these changes, the identity of the tuple stays the same, confirming that while the tuple cannot be altered, any mutable object stored inside it can be updated without creating a new tuple. Unpacking tuple values. Once you understand a tuple as an ordered package of related values, the next step is to unpack it efficiently. Unpacking means assigning each value in the tuple to its own variable in a single, concise operation, instead of accessing each position separately. By lining up variable names with the positions in the tuple, the language automatically assigns each element. This is especially helpful when the tuple represents a meaningful group, such as coordinates or a student record, because each part gets a clear, descriptive name. As a result, your code becomes easier to reason about, communicate, and maintain, with fewer chances for mistakes. Unpacking tuples is especially helpful when working with functions that naturally return several related values at once. For example, a function might analyze a document and return the total words, unique words, and average sentence length, which you can immediately unpack into clearly named variables. The same idea applies in areas like finance, where a transaction might return a status, code, and timestamp, or in sensor systems that provide temperature, humidity, and pressure together. By unpacking, you turn a compact tuple into labeled values that are easier to read, use in calculations, and base decisions on, without constantly remembering which position holds which piece of data. When working with tuples that may have different lengths, you can use flexible unpacking to keep your code clear. You pull out the key elements you care about, such as an identifier and a price, into their own variables, and gather any remaining elements into a single variable for optional metadata. This is especially useful with data feeds or logs where some fields are always present and others appear only in certain cases. It lets you keep tuples compact while still adapting to extra information and avoids repeatedly indexing into the tuple to reach important values. Python code, unpacking tuple values. This section explains how to work with tuple unpacking in a clear and practical way. It shows how to assign the elements of a tuple to separate variables using meaningful names, and how to unpack multiple values returned from a function into individual variables. It also introduces extended unpacking, where some values are assigned to specific variables, while the remaining values are collected together into a single variable for flexible handling. This comment explains that if extra libraries were ever needed, they should be installed using a package manager, but it also notes that the current code only relies on standard libraries. It serves as a reminder for developers to check and install any future dependencies. In this specific case, no additional libraries are required beyond what is already available by default. We create a tuple that stores 3 pieces of information: the number 12, the number 5280, and the text Central Park. Together, these values represent a location, where the numbers describe distance in miles and feet, and the text gives a descriptive name. Using a tuple lets us group this related data into one structure that cannot be changed, which helps keep it organized and easy to unpack later in the program. In this example, a tuple that holds miles, feet, and a place name is unpacked into 3 separate variables. Each value in the tuple is assigned to a clearly named variable that describes what it represents. This makes the data easier to read and work with in later code. By using descriptive variable names, you can access each part of the tuple directly, which improves clarity and maintainability. The code prints the values unpacked from the tuple to clearly describe a location. It begins with the word location, then shows the number of miles, the number of feet, and finally, the place name. The output is arranged so it is easy to read and understand what each value represents in the context of the location. We define a function called measureRoom that returns 3 values representing the length, width, and height of a room. In this example, those values are 12.5, 10, and 8. This single function call lets us quickly obtain all 3 dimensions at once. We can then unpack these values into separate variables for further use in our program. We are taking the 3 values returned by the measureRoom function and assigning them to separate variables for length, width, and height in feet. Each value in the returned group goes into its own variable. This lets us work with each dimension on its own, so we can more easily process or display them later in the program. This code prints the dimensions of a room using a formatted text message. It uses 3 values that represent the room's length, width, and height in feet. These values are unpacked into separate variables and then inserted into the message. The final output clearly states the room's dimensions in feet for all 3 measurements. We define a product tuple that stores a product identifier, its price, and some extra details in one place. The first element is a string for the product ID, followed by a floating point number for the price in dollars. The remaining elements are strings that hold additional information, such as promotions or availability. Using a tuple keeps this product data structured and easy to access in a single, unchangeable collection. In this example, extended unpacking is used to work with a tuple that stores product details. The first 2 elements of the tuple are assigned to variables representing the product ID and its price in dollars, which are the main pieces of information. All remaining elements, such as sales status or availability, are grouped into a list called extra details. This makes it easy to separate the core product data from additional information and handle each part as needed. The code extracts the main product information from a tuple by reading the product ID and its price. It then gathers any remaining values into a list as extra details. Finally, it prints a single formatted message that includes the product ID, the price in dollars, and any additional details, giving a concise summary of the product's information. This script shows how tuple unpacking works in Python to quickly assign multiple values at once. It first unpacks a location tuple into distance, smaller distance, and place name, then uses them in a descriptive sentence. It then defines a function that returns room dimensions as a tuple, unpacks them into length, width, and height, and prints them in a formatted message. Finally, It demonstrates extended unpacking by splitting a product tuple into main fields like product ID and price, and a separate group of extra details. Overall, it illustrates how tuple unpacking helps efficiently extract and organize related pieces of data. Python Dictionary Basics. Dictionary Key Value Pairs. In Python, a dictionary stores data as key-value pairs, where each key is a meaningful label linked to a specific value. This means you access information using descriptive labels, instead of relying on positions as you would with lists or tuples. For example, a student's information can be organized with keys like name and major. This structure matches how we naturally categorize information and makes managing data more intuitive. In Python, dictionaries store data as key-value pairs, which allows quick and direct access to information. Instead of relying on numeric positions, you use meaningful keys such as an email in a contact list or a product code in an inventory. This makes lookups faster and removes the need to remember index numbers. Using descriptive keys also makes the data more self-explanatory, easier to understand, and simpler to maintain. In a Python dictionary, each key must be unique because it refers to exactly one value, and if you assign a new value to an existing key, the old value is replaced. Different keys are allowed to share the same value, such as multiple product codes pointing to the same supplier. This structure makes dictionaries useful for organized records and lookup tables, where clear labels connect directly to specific pieces of information. By choosing appropriate keys and values, you can efficiently represent and access complex relationships in your programs. Python Code Dictionary Key-Value Pairs. This material explains a simple use of dictionaries as key-value pairs. It uses a small example of student information to show how data can be stored with labels. By printing the keys and their corresponding values, it demonstrates how related pieces of information are linked and accessed in a dictionary. This line is a placeholder comment reminding you to install any needed Python libraries. Before running the script, it marks where you might add a command to install a package using the standard tool for Python packages. Including such a reminder helps ensure all external dependencies are available. This supports code portability and makes it easier for others to run the script without missing libraries. We create a dictionary to store information about a student in a structured way. It has keys such as name, major, and graduation year, each linked to a specific value. For example, the name key stores Alex, the major key stores physics, and the graduation year key stores 2027. This lets us keep related details about the student together and access them easily when needed. The code prints the entire student information dictionary, showing all the stored key-value pairs at once. This lets you view the complete set of data associated with the student in a single output. It is a simple way to check what information is included and confirm that everything is present and correctly formatted. This line of code prints the student's name by looking up the value stored under the name key in the dictionary. It shows a clear label, then the key, and then the value it finds. This makes it obvious which piece of information is being displayed and what it represents. This line of code prints a label for the student's major and then shows the actual major stored in the dictionary. It does this by using the major key to look up the matching value. This demonstrates how to retrieve specific information from a dictionary and display it to the user. Here we add a new entry to the existing student information dictionary by giving it a minor field with the value physics. This shows that different keys in the same dictionary can share the same value. In this case, both the major and minor fields are set to physics. This is useful when multiple attributes of the same item need to reflect the same classification or characteristic. This code prints a message showing which keys in a dictionary share the same value. In the example, it points out that the keys major and minor both have the value physics. This illustrates that different keys can be linked to identical values. Such a structure is useful for organizing related pieces of data under different labels. This script shows basic dictionary use by creating a simple student record. It builds a dictionary with entries for the student's name, major, and graduation year. Then prints the whole dictionary and selected values like the name and major. It also adds a minor field that uses the same value as the major to show that different keys can share the same information. Finally, it identifies which keys have this repeated value, demonstrating how dictionaries can represent overlapping data. Look up values by key. Key value pairs are used to quickly find a value based on a specific key, similar to looking up a word in a bilingual dictionary. In computing, this might mean using a student ID to find a student's name, or a country code to find a country's name. Instead of searching through a long list, the system uses the key to directly access the matching value. This direct access makes key value pairs a very efficient way to retrieve data. When using a dictionary, you must look up values with exactly the same key that was originally stored, because even small differences like capitalization, spaces, or typos will cause the lookup to fail. For example, if email addresses are used as keys, a slight mistake in the address will prevent you from finding the correct record. If the key is not found, the dictionary cannot return a valid value. To ensure reliable lookups, it is important to standardize and validate keys so they always follow a consistent format. Dictionary lookups are a key part of many real-world systems, even when we do not see them directly. When a web service checks your login, it uses your username or email as a key to quickly find your stored credentials. A navigation app does something similar by using a street name as a key to find its coordinates. In data analysis, dictionaries map survey codes to descriptive labels, so numeric values can be turned into readable categories. Overall, this key-based lookup lets systems rapidly turn identifiers into useful information without scanning entire datasets. Python code, lookup values by key. In this lesson, we will look up values in a dictionary using simple student ID keys. You should show examples where a valid ID successfully returns the correct student information, as well as an example where an invalid ID fails to find a match. Use these cases to emphasize that dictionary keys must match exactly for a lookup to work. Also, highlight safe lookup methods that avoid errors when a key is missing, so the program can handle failed lookups gracefully. This line is simply a placeholder comment reminding developers that they may need to install a required library for the code to run. It suggests there could be a dependency, even though this particular script does not actually use any external libraries. Its main purpose is to prompt developers to check and install any necessary packages before executing the code. We create a dictionary that links each student ID to a student name so we can quickly find a name using the ID. This dictionary, called Students by ID, stores several pairs where each unique ID, such as A101, is matched with a specific student name, such as Alice. Using this structure makes looking up students by their ID efficient and straightforward. We begin by printing the entire dictionary of student records so we can view all stored key-value pairs at once. This shows each student ID matched with its corresponding name, making it easy to confirm that the data is mapped correctly. Doing this is a simple way to check the current state of the data structure and is especially helpful for debugging or verifying that the records are accurate. In this example, we look up a student's name in a dictionary using the student's ID as the key. We access the dictionary of students by ID with a specific key that we know is present. The dictionary returns the matching value, which is the student's name, and we store that result in a variable. This shows how a dictionary successfully retrieves a value when given an exact key match. This example shows the result of a successful dictionary lookup. The program uses a student ID, A101, to retrieve the matching name from the dictionary and stores that name in a variable. It then prints a message that includes the name found for this ID. This demonstrates how to correctly access a value in a dictionary using a valid key. In this example, we try to look up a student's name using a key that has different capitalization from the one stored in the dictionary. The key we use has a lowercase first letter, while the original key used an uppercase letter. This shows that dictionary keys in Python are case-sensitive, so keys that differ only by letter case are treated as completely different. As a result, trying to access the dictionary with a key whose capitalization does not match exactly will not find the intended entry. When working with a dictionary, you can use the get method to look up a value with a key that might be wrong or missing. This method is helpful because it does not cause an error if the key is not found. Instead, it returns a special value called none. This allows your program to keep running and gives you a chance to handle the missing key in a controlled way. The code tries to look up a value in a dictionary using a key that is not actually in the dictionary because its capitalization is wrong. It uses the dictionary's get method to search for this key. Since the key does not exist, the get method returns the special value none. This none value is then printed, showing that the lookup failed. The program first tries to get a student ID from the user by asking for input, such as A101 or B202. If something goes wrong during this input step and an exception occurs, the program catches the error instead of stopping. In that case, it automatically sets the student ID to A101. This approach keeps the program running smoothly even when the input process fails. We use the dictionary get method to look up a student's name based on an ID provided by the user. This method is helpful because we can also give it a default message, such as saying that no student was found for that ID. If the ID is not in the dictionary, the default message is returned instead of causing an error. This makes the lookup process safer and more user-friendly when an ID might be missing. The code displays the result of looking up a student ID. It prints a message that begins with the phrase indicating a lookup result, followed by the ID the user entered. After that, it shows either the matching student name from the dictionary or a default message if the ID is not found. This gives the user clear feedback about what happened with their input. This script shows how to look up student information in a dictionary using student IDs as keys. It first prints all stored student records, then retrieves a student's name with a correct ID to show that keys must match exactly. It demonstrates that changing only the capitalization of the ID causes the lookup to fail, because Python dictionaries are case-sensitive, and the safe get method then returns a value of none. Finally, the script asks the user for a student ID, tries to find the matching name, and if it is not found, returns a default message saying no student was found, illustrating safe lookup and graceful error handling. Adding dictionary items. Once you understand that a dictionary stores data as key value pairs, the next step is learning how to add new items so it can grow and adapt. This means you can create new keys whenever you have new information and assign values to them on the fly. This dynamic expansion is important for things like contact lists or configuration data, where you do not know all the entries in advance. Because of this, dictionaries let you efficiently store and retrieve information by name without needing to predefine every key. Adding items to a dictionary is useful because it lets your program adapt as new data arrives. For example, an online survey can store each response by linking a unique identifier to that person's data. In data analysis, you can track sales by linking product identifiers to their sales totals, adding new products and updating existing ones as needed. This flexibility allows the dictionary to grow and change with your program's needs without defining all possible keys in advance. When working with dictionaries, choose unique keys so you can access data efficiently later. If you reuse a key, its value will be replaced, which is helpful when updating information such as a current location or latest score. If you need to keep older data, you can include timestamps or version numbers in the keys, or store several values under a single key. Planning how you add and retrieve items helps keep your dictionaries organized and effective. Python code, adding dictionary items. In this lesson, we use simple contact examples to show how to add items to a dictionary. When you assign a value to a new key, the dictionary automatically creates a new entry for that contact. When you assign a value to a key that already exists, the dictionary updates the stored information for that contact. This demonstrates how dictionaries handle both creating new entries and modifying existing ones through key assignment. This line in the script is a placeholder for installing a library if needed. It represents a command to install a package, so the required library is available when the code runs. In this case, the line is commented out, which suggests the library is either already installed or not required for the current run. Including such a commented install command is helpful when sharing code, because it makes it easier to manage dependencies in different environments. We begin by creating an empty dictionary named Contacts to store phone numbers. In this structure, each contact's name serves as a key, and the associated phone number is the value. Using a dictionary in this way makes it easy and efficient to manage and look up contact information by name. This line adds a new entry to the contacts dictionary by using the name Alice as the key and her phone number as the value. In doing so, it creates a new key and value pair inside the dictionary. This allows the program to store and later retrieve Alice's contact information using her name. In this example, we add a new contact to a dictionary by using a unique key, Bob, and assigning it the phone number 555-0202. This creates a new entry that links Bob's name to his phone number. It shows how dictionaries store information as key-value pairs, making it easy to organize data and quickly retrieve or update it using the key. The code displays the current contents of the contacts dictionary after adding new entries for Alice and Bob. This output shows that the dictionary automatically updates as new key and value pairs are inserted. It illustrates how dictionaries can flexibly grow to store and organize additional data. By printing the updated dictionary, you can clearly see the new contacts included alongside any existing entries. In this example, we add a new contact to a Python dictionary by assigning a phone number to the name Charlie. Doing this automatically creates a new entry that links Charlie to the phone number 555-0303. This shows that dictionaries can be easily expanded just by using a new key and giving it a value. We display the current state of the contacts dictionary after adding Charlie to show that his information has been successfully stored. This output confirms that the dictionary now includes a new entry for Charlie. It illustrates that Python dictionaries are dynamic, allowing new keys and their associated data to be added easily at any time. In this example, we change Bob's phone number in the contacts dictionary by assigning a new value to his existing entry. Using the same key for Bob replaces the old number with the new one. This shows that when you assign a new value to an existing key in a dictionary, it updates the stored information for that key. This example shows that when you change the value associated with an existing name in a contacts dictionary, such as updating Bob's phone number, the dictionary immediately reflects that change. After assigning the new number, printing the dictionary displays the updated information. This demonstrates how modifying a value for an existing key directly updates the stored data. This script shows how to build and modify a simple contact list using a Python dictionary. It starts with an empty dictionary and adds entries for two people, each with a phone number, to demonstrate how new keys create new contacts. A third contact is then added to highlight that dictionaries can grow dynamically. Finally, the script updates one person's phone number by assigning a new value to an existing key, illustrating how dictionary entries can be changed. After each change, the current contents of the dictionary are printed so you can hear how it evolves over time. Working with dictionaries. Updating dictionary values. When working with dictionaries, an important task is updating the value for an existing key. You can think of each key as a label on a box, and the value as what is inside that box. Updating means changing what is inside without changing the label itself. For example, in an e-commerce system, you might update the status of an order by changing its stored value instead of creating a new entry. This lets dictionaries handle changing dynamic data efficiently and always reflect the most current information. Updating dictionary values is especially useful when working with complex data such as numbers, text, or nested collections. For example, a dictionary of student records can use student IDs as keys and store details like grades and attendance as values, which are updated as new information arrives. In a business context, a dictionary might map product codes to stock levels, adjusting quantities with each transaction. In both cases, the dictionary acts as a dynamic snapshot of the system's current state, supporting accurate decision-making and reporting. When multiple parts of a program share the same dictionary, any change to a value is immediately visible everywhere, because dictionaries are mutable. This is useful in situations like simulations or data analysis, where components may adjust shared settings or update raw data to cleaned or aggregated values. However, you must manage these updates carefully to avoid overwriting important information or creating inconsistencies. Clear, well-chosen keys and good documentation of changes help keep the dictionary understandable and reliable over time. Python code: updating dictionary values. This section focuses on updating values in a dictionary that represents simple inventory quantities. The goal is to show that when you change the quantities, the keys and overall structure of the dictionary stay the same. You should print the dictionary before making changes and again after the updates. This clear before and after view helps you visualize exactly how the dictionary's values change while its keys remain unchanged. The line with the exclamation mark and the install command is a placeholder for installing any libraries the script might need. Developers often put such a line at the start of a script to make sure all dependencies are available. In this case, the line is commented out, which means no extra libraries are needed right now, or the required ones are already installed. We represent a store's inventory using a dictionary that maps item names to their stock levels. Each item, such as apples, bananas, and oranges, is used as a key, and its current quantity is stored as an integer value. For example, apples might have a quantity of 10, bananas 6, and oranges 4. This structure makes it easy to track and update how many of each item are in stock. We begin by displaying the original inventory dictionary so we can see the starting quantities for each item. This gives us a clear baseline before any changes are made. By knowing these initial values, it becomes easier to compare and understand the updates that will follow. We update the number of apples in the inventory by first reading the current amount stored under the apples key in the dictionary. Then we add 5 to this value to represent a new shipment. Finally, we store this new total back under the same key, so the apple count increases while the overall dictionary structure stays the same. This line updates the number of bananas in the inventory dictionary by taking the current value stored under the bananas key and subtracting 2 to represent a sale. The result is then stored back under the same key. This way, the structure of the dictionary stays the same, but the quantity of bananas is correctly reduced. We can add a new item to an inventory dictionary by assigning a value to a new key. In this example, we create a pears entry and set its quantity to 7. This updates the dictionary to include pears and records the current stock level for that item. Using this method, we keep the same dictionary structure while easily expanding the inventory with new products. We finish by printing the updated inventory dictionary to show the new quantities for each item. This final output clearly displays how the inventory has changed after modifying the values for apples and bananas and adding a new entry for pears. In other words, the print step confirms the current state of the inventory after all updates have been applied. This example shows how to change values in a dictionary while keeping its overall structure the same. It starts with an inventory that tracks quantities of apples, bananas, and oranges, then increases the number of apples to represent a new shipment, and decreases the number of bananas to represent sales. It also adds a new fruit, pears, with its own quantity. The updated inventory is then printed to show that the keys stay the same, while the values can be modified and new entries can be added as needed. Looping through dictionaries. When working with dictionaries, it is often important to process every entry, not just individual values. So looping becomes essential. By iterating through a dictionary, you visit each key and its associated value to read, analyze, or modify the data. This lets you inspect all details in structures like a student profile or a product inventory. Iteration is especially useful because it works even when you do not know how many entries there are or what the specific keys will be in advance. When looping through a dictionary, you can choose to work with just the keys, just the values, or both together, depending on what you need to analyze. Focusing on keys is useful when you care about the labels, while focusing on values helps when you are analyzing the data itself. Looking at key and value pairs together lets you understand how each label relates to its data. In every case, the loop follows the same basic pattern. Retrieve an item, do something with it, then move on to the next one until all items are processed. Looping through dictionaries is important when you need to systematically update or transform stored data, such as adjusting customer loyalty points or changing task statuses in a project management tool. As you iterate, you must be careful about how adding or removing entries can affect the dictionary structure. To avoid problems, a common approach is to record any changes you want to make while looping, then apply those changes after the loop finishes. This helps keep the iterations stable and ensures every key and value is processed correctly. Python code looping through dictionaries. In this lesson, you will learn how to loop through a dictionary by accessing its keys, its values, and its key-value pairs. You will practice reading the data stored in a dictionary and printing it in a clear, formatted way, so the output is easy to understand. You will also see how to safely update dictionary values while looping by first collecting the changes in a separate dictionary and then applying those updates afterward. Together, these skills help you work with dictionary data efficiently and without errors. This line is simply a placeholder comment indicating that you could install an extra library if needed, but in this case, it is not necessary. It explains that the built-in standard library already provides everything required for the script. As a result, no additional installation steps are needed to complete the task. We represent the store's inventory using a dictionary that maps each product name to its current stock level. In this structure, items like apples, bananas, oranges, and milk act as keys, and their quantities are stored as numbers. For instance, apples might have a stock of 12, while oranges could have a stock of 0, meaning they are out of stock. This approach makes it easy to look up and update the stock level for any product in the store. We begin by printing a simple header that says Products Available. Then, we loop through the dictionary of items using its keys, which are the product names. For each product name, we print it with a dash in front. This creates a clear, easy-to-read list of all products currently in stock, without yet showing how many of each item there are. We first print a simple header to show that we are about to list only stock counts. Then we go through each value in the dictionary that stores product stock levels. For every stock value, we print the word count, followed by the number of items available. This lets us review inventory quantities clearly without mentioning any product names. We display a header that says Detailed Inventory to introduce the information, then go through each entry in the product stock dictionary. For each product, we take its name and stock count, capitalize the product name, and print it with the number of units followed by the phrase units in storage. This creates a clear, organized summary of how many units are currently available for each product. We begin by creating an empty dictionary called Stock Updates that will temporarily store any changes we want to make to product stock levels. This separate dictionary is used while we loop through the original stock data. By keeping updates in a different place, we avoid changing the original dictionary during the loop. This helps prevent errors and unexpected behavior that can occur when modifying a collection as you iterate over it. We loop through each product and its stock level in the dictionary and decide how to update it. If a product has 0 stock, we plan to restock it to 10 units, and if its stock is below 6, we plan to add 3 units. Instead of changing the original dictionary while we loop, we record all these planned updates in a separate dictionary. This way, we can safely apply the changes after the loop finishes without causing errors or unexpected behavior. After we calculate all the necessary stock changes, we loop through the updates, and for each product and its new stock level, we modify the original stock record. By applying all updates only after the calculations are finished, we keep the original data consistent and avoid errors during the update process. We first print a message to signal that we are about to show the updated inventory after restocking. Then we go through each entry in the product stock dictionary, get the product name and its current quantity, and print them in a clear, formatted way. The product name is capitalized, and the number of units in storage is shown, giving a concise and readable summary of the new inventory levels after changes have been applied. This script shows how to loop through a dictionary that represents a store's product stock in order to read and update its contents. It first goes through the dictionary to print all product names, then their stock counts, and then a combined inventory list with each product and its quantity. It also demonstrates a safe way to change dictionary values while iterating by collecting updates in a separate dictionary. Using this approach, it restocks items with 0 units to 10 and increases the stock of items with fewer than 6 units by 3. Finally, it prints the updated inventory so you can see the changes made during the loop. Checking membership. When working with dictionaries, you should always check whether a key exists before trying to use it. You can think of each key as a label on a box that holds a value, and you need to confirm the box is there before opening it. For example, if you store student grades by ID, first verify that the ID is present before updating the grade. This prevents runtime errors and lets you handle missing data more safely, such as by using a default value or recording a warning. When working with dictionaries, it is important to distinguish between checking for a key and checking for a value, because dictionaries are organized around keys. In most cases, you care about whether a key exists, since keys allow fast lookup and updates. For instance, in a bookstore inventory, you would first confirm that a book's identifier is present as a key before changing its stock level, which helps avoid errors from missing entries. In contrast, searching for a particular value, such as all items with 0 stock, is less efficient because it requires scanning through all stored values instead of using quick key access. Membership checks are important for controlling program behavior and improving user experience, especially when data may be incomplete or changing. For example, in a web app that stores user preferences in a dictionary, checking whether each preference exists lets the app fall back to default values instead of crashing. In data analysis, confirming that required keys are present ensures that only complete data is processed. Overall, these checks make programs more reliable and better able to adapt as data structures evolve. Python code. Checking membership. This material focuses on how to work with dictionary keys safely and clearly. It shows how to check whether a key is in a dictionary before using it, and how to read values in a way that avoids errors when a key might be missing. It also highlights that the behavior should differ depending on whether the key is present or absent, such as returning the stored value when it exists or using a safe fallback when it does not. Overall, the goal is to demonstrate simple, practical patterns for handling both existing and missing keys in dictionaries. In this example, we do not need to run any pip install commands because the code does not depend on external libraries. Everything it uses is already available in a standard Python environment. This makes the example simple to run and removes the need for extra setup steps. As a result, you can focus on the code itself without worrying about installing additional packages. We create a dictionary called Student Scores to store test results, using each student's ID as the key and their score as the value. In this example, the student with ID A123 has a score of 88, B456 has 92, and C789 has 75. Organizing the data this way makes it easy to quickly look up any student's score using their ID. We set a variable to the student ID A123, which we already know exists in our dictionary of student scores. This prepares us to look up that specific student score. Because the ID is known to be present, we can safely access the score without causing an error from a missing entry. In this example, we choose a student ID that does not appear in the dictionary, labeled as a missing ID and set to Z999. Using an ID that is not present lets us show what happens when the code tries to access a key that does not exist. This setup is useful for demonstrating how error handling works and how default values can be used when a lookup fails. We first check whether the stored student ID exists as a key in the student scores dictionary using a membership test. If the ID is present, we then print a message that includes both the ID and its associated score from the dictionary. This approach ensures we only access a score when the ID is valid, which helps avoid errors caused by trying to use a key that is not in the dictionary. We first check whether the student ID stored in the missing ID variable exists in the dictionary of student scores, using a membership test that efficiently looks for that key. If the ID is present, we then print a message that includes both the ID and its associated score from the dictionary. This approach ensures we only access a score after confirming the ID exists, which prevents errors that would occur if we tried to use a key that is not in the dictionary. In this part of the program, we handle the case where a student ID is not found in the dictionary of scores. The else branch runs when the earlier condition that checks for the ID fails. When that happens, the program prints a message saying the student is not in the score records. This makes it clear to the user that the lookup did not succeed and provides helpful feedback instead of failing silently. When a student ID might not be in a dictionary, you can use the dictionary's get method to safely look up the score. This method tries to find the value for the given ID and, if it is missing, returns a default message such as "no recorded score yet." Using this approach avoids writing a separate check to see if the ID exists. It keeps the code cleaner and provides an efficient way to handle missing keys. This code looks up a student ID in a dictionary and shows what happens when the ID is missing. It uses the dictionary's get method, which lets you provide a default value if the key is not found. Here, the default is a message saying there is no recorded score yet for that student. This avoids doing a separate check for whether the ID exists and clearly indicates the result when a key is absent. This script shows how to safely check for keys in a dictionary and handle missing data. It uses a dictionary where student IDs map to test scores, then checks whether a given ID exists before printing the score. If the ID is not found, it prints a message saying the record is missing. It also demonstrates using the dictionary's get method to request a score for a missing ID and return a default message instead of causing an error. This provides a clear and graceful way to manage absent keys in a dictionary. In this lecture, you learn to define and use tuples to store small ordered groups of related values, create dictionaries to map keys to values and access items by key, and update and iterate over dictionaries to read and modify stored data. In the next module, Module 5, we will go over functions basics.
Thank you for your attention. See you all in the next lecture.